Welcome to our AP Precalculus lesson on Topic 1.6, where we will explore a fundamental concept for understanding polynomial functions. Today, we're focusing on polynomial functions and their end behavior. Our main goals for this video are to define end behavior, understand how a polynomial's leading term determines it, and learn to identify the four main cases based on the degree and leading coefficient. By the end of this lesson, you'll be able to quickly sketch the overall shape of any polynomial graph. First, let's define what we mean by end behavior. End behavior simply describes what happens to the function's output, p of x as the input x, gets extremely large or extremely small. In other words, we want to know what happens at the very ends of the graph. We analyze this by looking at the limits as x approaches positive infinity and as x approaches negative infinity. The notation for this is the limit of p of x as x approaches infinity, and the limit of p of x as x approaches negative infinity. For non-constant polynomials, which are essentially any polynomials with an x term in them, the end behavior is always very simple. The outputs will either increase or decrease without bound, heading towards positive or negative infinity. So, how do we figure out this end behavior? That brings us to our next key principle. The leading term determines end behavior. Any polynomial, like the one I'm writing on the board, is made up of several terms. In this general form, a sub n x to the n plus a sub n minus 1x to the n minus 1, all the way down to the constant term. The leading term is the one with the highest power of x. It consists of the leading coefficient, a sub n, and the highest power of x, x to the n. This single term is the only one we need to consider when looking at end behavior. Why is this the case? It's because as the absolute value of x gets very, very large, the term with the highest exponent dominates all the other terms. The lower degree terms become negligible. Let's see this with an example. Consider p of x equals 3x squared plus 2x plus 5. For small values of x, like x equals 1, the terms are all significant. We have 3 plus 2 plus 5, which equals 10. But what happens when x is very large? Let's try x equals 100. Here, p of 100 is 3 times 100 squared, plus 2 times 100 plus 5. This calculates to 30,000 plus 200 plus 5, which is 30,205. Notice that the leading term, 30,000, is far, far larger than 200 or 5. It's doing almost all the work in determining the output value. So, to determine end behavior, we just need to analyze the sign of the leading coefficient and the degree of the leading term. We can categorize all end behaviors into 4 cases based on just 2 pieces of information: the degree and the leading coefficient. These are our degree and leading coefficient cases. Let's first define these terms. The degree of the polynomial is the highest exponent. The leading coefficient is the number multiplied by the term with the highest exponent. We'll be looking at whether the degree is even or odd, and whether the leading coefficient is positive or negative. Let's build a mental model for this. Think about the most basic even and odd functions you know, y equals x with 2 and y at x 3. First, the even degree case. The most famous even degree polynomial is y equals x squared. Both ends of this graph point upwards. This is our first rule. Case 1. Even degree, positive leading coefficient. The end behavior is up on both the left and the right. This is because a positive coefficient doesn't change the direction of x squared, which is always positive for large x. Now, what if the leading coefficient is negative? This is like flipping the graph of x squared over the x-axis. For example, I equals negative x squared. Now, both ends point downwards. Case 2. Even degree, negative leading coefficient. The end behavior is down on both sides. A negative coefficient makes x squared negative. It's important to remember that all even degree polynomials, whether it's x squared, x to the 4th, x to the 6th, and so on, have this same end behavior. The ends will either both go up or both go down. Now let's move on to the odd degree cases. Again, we'll start with a basic example. The simplest odd degree polynomial is y equals x cubed. This graph behaves differently. The left end goes down and the right end goes up. This is our rule for a positive leading coefficient. Case 3. Odd degree, positive leading coefficient. The end behavior is left down, right up. As you move from left to right, the function generally rises. This is called increasing end behavior. Finally, let's consider a negative leading coefficient for an odd degree polynomial. This is like reflecting y equals x cubed across the x-axis. Look at y equals negative x cubed. Now, the left end goes up and the right end goes down. Case 4. Odd degree, negative leading coefficient. The end behavior is left up, right down. As you move from left to right, the function generally falls, so we call this decreasing end behavior. Just like with even degrees, all odd degree polynomials follow this pattern. If the degree is odd, one end will go up and the other end will go down. To summarize, the key question is always, does the graph end in the same direction on both sides or in opposite directions? Even degrees mean same direction. Odd degrees mean opposite directions. The sign of the leading coefficient tells you what those directions are. Let's put this all together into a summary table, which I'm now displaying on the screen. This table is your cheat sheet for end behavior. It organizes the 4 cases we just discussed. Let's work through a few examples to see how to use this table. Example 1. F of x equals 2x to the 5th power minus 3x cubed plus 7. The first step is always to identify the leading term. Here that's 2x to the 5th power. From this, we see that the degree is 5, which is an odd number, and the leading coefficient is 2, which is positive. Looking at our table, we find the row for an odd degree and a positive leading coefficient. It tells us the left end goes down and the right end goes up. Let's try another one. Example 2. G of x equals negative 4x squared plus x minus 10. The leading term here is negative 4x squared. The degree is 2, which is even, and the leading coefficient is negative 4, which is negative. Consulting our table, the row for an even degree and a negative coefficient tells us both ends go down. The beauty of this rule is that it works even when the polynomial is not in standard form. Consider this factored form. H of x equals x minus 1 times x plus 2 times x minus 5. You don't have to multiply this all out. Just think about what happens when x is very large. In each parenthesis, the x term will dominate the constant term. So, for end behavior, h of x behaves like x times x times x. This gives us a leading term of x cubed, which has an odd degree of 3 and a positive coefficient of 1. Therefore, the end behavior is left down, right up. As you can see, you only need to multiply the leading x's from each factor. Let's look at one more slightly tricky case. What about k of x equals negative 2 times the quantity x minus 3 squared times x plus 4? Again, let's analyze the leading terms of each part. We have a negative 2 outside. The x3 squared term will behave like x squared, and the x plus 4 term will behave like x. So the end behavior of k of x will be like multiplying negative 2 times x squared times x. This simplifies to negative 2x cubed. The leading term is negative 2x cubed, which has an odd degree of 3 and a negative coefficient of negative 2. Therefore, the end behavior is left up, right down. Notice how the negative 2 from outside the parentheses was a part of the leading coefficient. So, let's quickly recap what we've covered today. We learned about the end behavior of polynomial functions. First, we defined end behavior as what happens to the function's output as x approaches positive and negative infinity. This is the behavior at the graph's extremes. Second, we established the leading term rule, which says that only the term with the highest power of x determines this behavior, as it dominates all other terms for large x values. Finally, we explored the 4 cases that govern end behavior, based on whether the degree is even or odd, and whether the leading coefficient is positive or negative. We saw that even degrees lead to ends going in the same direction, while odd degrees lead to ends going in opposite directions. By following these simple rules, you can determine the end behavior of any polynomial function. The key is to identify the leading term and then use the degree and coefficient to pick one of the 4 cases from our summary table. This is a powerful tool for sketching polynomial graphs. I hope this video has helped you understand how to analyze the end behavior of polynomial functions. Thank you for watching.